focus. Christos is a postdoctoral researcher at Computer Vision Lab at ETH Zurich. His broad research fields are computer vision and machine learning, and the focus of his research is on high level of visual perception, with emphasis on their applications of autonomous cars and robots. And since 2021, he has been a principal engineer at Trace Zurich, and today he will be presenting optimizing internal network representations for geometric and semantic perception. Christos, please take away.
Hi, everyone. It's very nice to take part in this workshop, which combines the topic of learning representations with autonomous driving. Since there has been an introduction, I will directly go to the content of the talk. I start from the observation that there is empirical evidence, according to previous publications, that vision cues such as depth and semantics, so semantic segmentation, are beyond further utility in vision tasks. They're also the most vital cues for action in the context of autonomous cars or robots. So both of these tasks share the same feature, that they are a dense perception task. So we need to output a prediction at each separate pixel of our input image. So typically, what most works do for such dense perception tasks, whether geometric or semantic, is that they adopt an encoder-decoder pipeline. In this case, I'm showing an example for semantic segmentation, where the input image passes through the encoder. In that part, we have aggregation of context across different regions of the image, and the network tries to abstract away from the low-level textures and other cues like edges in the image to higher-level concepts and extract the relevant information for these concepts. So we have then the decoder, where we need to basically go back to the original resolution that we had in the input, so typically a high resolution. And there we want to use the features that are output from the encoder in order to completely parse the image, whether this refers to semantic classes or parse it with respect to the values of a continuous quantity, such as in the case of geometry, the depth value, or the values that define the normal vectors of the surface. Now we see that in this pipeline, which is very widely used, there is this internal representation, this internal feature map at the interface between the encoder and the decoder. And we can claim that it constitutes an information bottleneck, where basically all the information and the data that we have in the input image needs to pass from that point in order to be used later on for generating the predictions. So in this talk, the key theme that I will cover is the optimization of internal representations of this bottleneck level representations at the interface of the encoder and the decoder of a network, optimize them directly, either with specialized modules or with dedicated losses, in order to inject further priors or better architectures for dense geometric and semantic perception tasks that are relevant for action, in particular for autonomous cars. So I will cover the two parts. One is about the geometric perception, where I will present our recent work titled Internal Discretization for Monocular Depth Estimation, which is to appear in CVPR23. And then I will go on and cover the second part about the semantic perception. So here I will focus on the fundamental task of semantic segmentation, and I will present two recent works that we have. One is the condition invariant semantic segmentation, which is currently under review, and the other one is the contrastive model adaptation for cross-condition robustness in semantic segmentation, which you can find in arXiv. And both of these semantic oriented works focus on the setting where we don't have full supervision to perform the task in our target domain. So we have some kind of domain adaptation that we will review later. So this brings us to the first part, the first main part of the talk, which is about our internal discretization model for geometric perception. We can see the overall architecture of our model. So as we saw previously, we also adopt the standard encoder-decoder pipeline in the left. And at the interface of the two parts of the network, we have these features we denote by F. So these are three-dimensional feature maps. And these features are then passed to the standard decoder in order to obtain pixel-level embeddings. Now, the core contribution in this work is the introduction of a continuous, discrete, continuous bottleneck, which is denoted here with the multiple orange boxes. This module we call the internal discretization module, and it basically enforces the internal representations that the basic network, encoder-decoder network, extracts to be clustered in a soft input-dependent manner into different abstract level, high-level abstract concepts. And we will see actually later after presenting the method, how this can be actually realized for example scenes and actually make sense for us humans that they can be clustered into meaningful concepts. So first, I will talk about the continuous to discrete part of the internal discretization module. So this part basically applies what we call the transposed cross-attention operation. This is what is shown on the left-hand side equations. So instead of the normal cross-attention operation or the general attention operation, where basically we have a softmax of the matrix of the queries Q times the matrix of the keys K transpose. Here we take the transpose of this matrix, we then apply the softmax, and afterwards we take again the transpose. So basically what we do in this way is that we enforce and we encourage competition between the different queries which come from the priors that we want to cluster our scene into. These are the H prior symbol, and these priors are basically adaptive or input dependent priors, so that we don't have like randomly initialized priors in this case. So this was about the adaptive feature partitioning part, which is the continuous to discrete module of our internal discretization part. And then the second module is the internal scene discretization, actually what we can do to bring it back to the continuous space from the internal discrete representations that we have obtained. So this module takes the learned internal discrete representations from the adaptive feature partitioning part, and it computes their similarity via, again, a normal attention operation to the dense pixel level embeddings that are output by the standard decoder of the network. And in doing so, we're able to localize in the output space of the pixel embeddings where each internal discrete representation has the most influence, which is also illustrated in the figure with the different soft color maps on the image. So coming on to the results for our internal discretization method, I will mostly focus on results on outdoor datasets, since we are more interested in this workshop in the autonomous car setting. So we have compared to the previous state-of-the-art approaches on the standard KITI benchmark. And we basically also introduce a new metric, which is just a different instantiation of the delta, of the very standard delta metric, but we somehow change the threshold about the inliers in order to have more meaningful comparisons, so that all the methods do not saturate close to 100%, as was done with the delta 2 or even the delta 3 metric that we don't show here. So in this comparison, we can see that we have a clear benefit compared to previous state-of-the-art approaches. And this is true also for different backbones. So we use like a ResNet backbone or a swing transformer backbones or efficient net backbones. And still, we see that for this different variety of basic networks, we can always get significant improvement. And I would like to note at this point that we have also submitted the results of our method on the official depth estimation KITI benchmark, and we are among the 2 top published methods in the benchmark, and the 4th overall, including unpublished methods. Besides depth estimation, we have also experimented with the alternative surface normals estimation task, which is also a geometric-based task. And without any modifications in the training architecture or procedure, so with the same setting and without any specialized modules for this different task, we are able to significantly outperform the previous state-of-the-art, which was especially designed for the surface normals task across all different metrics. Qualitatively, our results are also very satisfactory on the KITI dataset. So, for example, in the bottom image here, we see a very complex scene with a lot of pedestrians, and the pedestrians are distributed across different parts of the range of depth values. So you can see that other recent state-of-the-art competing approaches are not that successful in distinguishing the different depth values for the various pedestrians. You can see that the colors of the pedestrians in the depth maps are more uniform across the different instances of this class, whereas in our case, we are able to finally distinguish between the distance for each pedestrian in the crowd. We're also able in the top image to have a better separation between the background, which has a much higher depth value, and the foreground objects, which are the cars that are evident there. And I promised you before that we can see, actually, we can visualize what these internal discrete representations are assigned to in terms of this concept. So we see here, each row of the figure corresponds to a different token in our transpose cross-attention, so a different query. Therefore, it's like the same discretized representation, and then across the different columns of the figure, we see different images. But it's the same query across the different images. So we see that in the first row, we learn a concept that there is like a part of the image at the center or the upper part, which is background, so it has a higher depth values. At the bottom row, on the contrary, we see that with the yellow color corresponds to high attention values for the corresponding representation. So we see there that the model learns to basically discretize together edges in the depth map that correspond to part which is closer at the lower part of the edge, so horizontal edges, and the part that is further away in the upper part of the edge. This concludes the first part of the talk, and now we'll continue with the second part for semantic perception. So first, I will talk about our condition invariant semantic segmentation method. So here is the complete overview of the method. We consider an unsupervised domain adaptation setup, where we denote the source domain by S and the target domain by T. And we see here in our architecture, we can have input images, IS and IT, to the network from both domains. And our network also includes, our model also includes non-learned stylization module, G, which basically applies a shallow stylization operation to transfer the style of the target image IT to the source image IS. So, and vice versa. So we can have like stylized versions IS to T with the content of the source image and the style of the target image, and stylized images IT to S with the content of the target image and the style of the source image. Now, the idea here is to enforce consistency between the representations that the network learns for the different versions of the same image, which each image has different style. But previous works almost always consider consistency of these representations at the level of network outputs. And of course, why I'm showing this work is because here we propose to impose invariance at the level of internal representations. So this feature maps phi that we see in the middle of the network between the encoder and the decoder. The reason we do this is that we want to encourage the encoder to abstract away from the domain for the particular domain of the input by extracting internal representations that are already invariant to the style of the input, and to allow the decoder, thus allow the decoder to focus only on parsing these representations and not having to further abstract from the specific style of the input based on the representation that it gets from the encoder. So to formulate the approach better, we have our network F, which is the composition of a encoder phi and a decoder omega. So for an input image I, the encoder outputs d-dimensional features with m height and n width. And we have our feature invariance loss, which is defined as the Frobenius norm of the difference between the feature maps for the input image and the reference image I prime. So we have here different baselines. One might ask, okay, why do you need the feature invariance loss in any case? Because you can alternatively also supervise your network for the prediction of the stylized image, and you don't need to consider the features of the stylized image. So this is what is done in the Fourier domain adaptation loss, where basically the authors propose to supervise the stylized image IS to T from the source to the target domain, and also supervise as well the prediction for the target image IT with the pseudo labels that we have Y hat T. And finally, one could go even further and propose to formulate a loss with all the possible cross-entropy terms. So for the 4 inputs of the network, the 4 different images at each batch, at each example, we can compute the cross-entropy loss for the predictions of the network for each of these 4 images. So this would be our baselines that we will also compare in the ablation study that will follow. And instead of this, our formulation, our proposed formulation for the KISS method, the condition invariant semantic segmentation, states that we need to only take the cross-entropy losses with the labels or the pseudo labels for the original images without stylization. And on top of that, we can also apply our invariance, our feature invariance loss between the internal representations of corresponding pairs of images with the original version and the stylized version. And this can be done for the source domain. So we have a term multiplied by lambda s, a hyperparameter for the source domain, and another term for the target domain with another hyperparameter lambda t. And now you may ask, okay, but what if we use anyway this consistency at the prediction level? So we have tried that in order to show that it actually makes sense to impose invariance in the internal representations. So here in this figure, we show the case of comparing validation set performance on the cityscapes to ACDC adaptation using the feature invariance loss only in the source domain. So we just have the term with the lambda s value for the hyperparameter, and we vary this hyperparameter to see what happens for different values of it. So the red curve with some confidence interval stands for the performance of the final network on the validation set when we take invariance on the prediction, so at the decoder outputs. Whereas the blue curve corresponds to invariance at the internal representations. And higher is better here. So we see that we can have a significantly improved performance at the rightmost part of the curve for the internal representations when we apply the invariance, whereas when we apply invariance at the predictions, the performance already deteriorates for quite low values of our loss, quite low weights for our loss. So this is the ablation study that I promised before, where we see that we can actually perform much better than the different baselines. So the baseline for the FDA type of loss is the second line, which already gives an improvement over the basic baseline, which just uses the cross entropy on the original images, so no stylization involved. And compared to the FDA baseline or baseline 1, our invariance loss in the source domain only, which is row 4 of the table, gives a further boost in performance, going around 66.5 or 67% mean IOU on the validation set. So 1% better than the FDA baseline already. And we see the same trend in the target domain. So in the second part of the table, where if we only apply our invariance loss in the target domain, we also have a significant boost in performance from the basic baseline from 64.1 to 66.9. And finally, combining both losses in the source and target domain achieves the best performance. And we see that these two losses actually synergize to give us like a significant 4% improvement with also low variance in the final model performance across different training rounds. So I don't want to bother you a lot with numbers, but just as a brief overview of the comparison to the state of the art. So we have compared thoroughly to previous domain adaptation approaches on the Cityscapes to ACDC benchmark for different conditions. And we improve significantly also consistently among most classes. We have in particular significant improvements in traffic-related classes such as traffic light and traffic sign, where we are roughly 2 to 5% better than the previous best approach. And we also have a significant improvement at the also traffic-related sidewalk class at least 12 or roughly 12% mean IOU better than the previous best approach. So I think what is more interesting here are the qualitative results. So for the ACDC, we have a variety of adverse conditions, and you see that the previous state-of-the-art approach fails on the sky class. Here it predicts it as road. Then on this difficult nighttime image, you see in the ground truth in the second column, we have some very hard to see pedestrians, which are denoted by red. The baseline approach, also competing method, fails to detect them. We are able to detect this pedestrian and also a very far away motorcycle, which is even impossible to see by bare eye. And also we see that we have better performance on the segmenting class from the segmenting sky from vegetation at nighttime images. And finally, in the case of rain, we might have some reflections on the ground, which correspond to traffic lights that are green and are reflected to the camera, whereas in our case, we are able to segment this correctly as road, and we're not fooled by the reflections. And I will very quickly come to the last part of my talk, where I will cover our work on contrastive model adaptation, or CMA, for cross-condition robustness in semantic segmentation. Here, instead of the standard unsupervised domain adaptation setting, where we assume that there are also target domain images available at training time, here there are no, when there are source images available at training time. In this case, we don't have any source images available at training time. We only have a model that has been trained on the source domain, and we further have target domain images, which we want to train our model and adapt it on. Now, for this particular work, we make a key assumption. We assume that for each target image, we also have
Yes, he's completely out of the zone now.
Okay. Oh, now he's back. Okay.
Yeah. Sorry, I was disconnected. Sorry for that. Let me share my screen again. Did you already hear about this slide, or was I disconnected before reaching this point? From here. Okay, great. So let me continue. So we basically have our encoder-decoder again, the usual setting that we have seen already. And we freeze completely the encoder in the sense that we don't want it to learn new concepts from the model that has been trained already on the source domain. We just want to be able to, my mistake, we completely freeze the decoder because we have already learned how to parse certain classes. So the classes do not change in this setting, just different conditions. So no difference in the semantics of the classes or the different prototypes. We just learn the encoder, and the rest we keep frozen. And basically how it operates, so we have two different images of roughly the same scene, but under a slightly different viewpoint. So we have also a warping module, which allows us to align the features from the one image, like with the source, with the normal condition, to the view of the adverse condition image. Here I just present the semantic labels for easier visualization, but we operate with this warping at the internal space of the features. And then we employ contrastive learning. So basically we take patches of the adverse condition image that we use as anchors. This is in black. Then all the other patches in the same image corresponding to different locations are negatives in the contrastive learning framework. And the patch that corresponds to the anchor in the reference image from the normal condition is the positive. And this is how we formulate our novel cross-domain contrastive loss, which is basically an instantiation of the very widely used normalized temperature scale cross-entropy loss from the SIM-CLR paper by Hinton et al. So we said before that we have this misalignment between the reference image and the target domain image. So we use a warping from our previous work of ours called Refine in order to align the two feature maps. And this warping also gives us a confidence that I present here with the white color in the middle columns. The white color means that there is not, the confidence value is lower, whereas where you can see, and actually it is transparent and you can see the image, the confidence is higher. So we use this confidence values as weights to get our vectors for the contrastive loss. So A are the anchors, P are the positives, and we basically average across each patch the individual feature vectors at each position, taking the corresponding confidence as the weight. And this is how we formulate our contrastive loss across the different patches I. So we compute the cross-domain contrastive loss for each patch, and then we sum over all different patches of the target image. With this cross-domain contrastive loss, we're able to better separate the internal feature space. So here I show a TSNE visualization with only 4 classes, just for easiness of visualization. Without the cross-domain contrastive loss, you see that the representations of different classes are not clustered together in the feature space. So you see that, for example, the sky in the left part, without the CDC loss, has 2 different clusters, which are disconnected, and they have vegetation in between. Vegetation samples in between, whereas with the cross-domain contrastive loss, we're able to better cluster into coherent groups the pixels from the different classes in this feature space. And again, I will not go into the full quantitative comparisons, but just as, let's say, a teaser for you to also read the paper more thoroughly, I can already tell you that even in the case where we want to generalize, so we have trained, for example, on cityscapes to ACDC, our model adaptation. And then we take this model and we evaluate it on a completely different benchmark. We have compiled a benchmark called ACG from different existing datasets with adverse conditions. And we compare both with model adaptation approaches, which are marked with a tick, with a check mark in this table, and with standard unsupervised domain adaptation approaches, which are at an advantage with respect to us. And we see that we actually can generalize even better, not only compared to the source-free, to the other source-free approaches, but also to the privileged domain adaptation approaches. So that's all from my side. I'm really happy to take questions at this point.
Thank you, Christos. Let's give him a round of applause. Any question from the audience? So we also have a panel discussion with Christos being one of the panelists. So if you have any questions, we can ask him later. But due to time constraint, we're going to move on to the next talk. So next talk is by Professor Bo Li. She is an assistant professor in the computer science department at the University of Illinois at Urbana-Champaign. She is on the advisory board of the Center for Artificial Intelligence Innovation at Illinois and a member of the Information Trust Institute. Her research focuses on trustworthy machine learning with an emphasis